Good morning, guys.
Morning.
Morning.
Good morning.
How are you? Sorry, I couldn't make the review session yesterday. So you have I uploaded guidelines for the exam too. Did I miss anything? Do you have any other questions? Okay. Do you have any questions before I start the review session? I'm planning to go over chapter 4 up to chapter 7. So the exam will cover chapter 4 to 7. So 8 will not be in the exam. 14 will not be in the exam. So there is no much material you need to go over it before the exam. Okay. Any questions before I start? Okay. So let me set up my computer. Okay. Do you see my screen?
Yep, we can see it.
Okay. If you have any question at any time, please unmute yourself and ask the question at any time. So let me go over chapter 4 up to chapter 7. So for each chapter, you need to be familiar with some stuff. So let me go over these ones first. To chapter 4 to chapter 7. For each chapter or for each design will be covered in these chapters. There are many designs covered in this chapter. For each design, you need to be familiar with the requirements. The requirements of each design. You need to be familiar with the assumption of each model or the assumption of each model of each design. But the assumptions are the same. The assumption on all of them, independence normality, and constant variance. You should be able to tell the assumptions are satisfied by graphs and also by tests like independence, Durbin-Watson, normality, Shapiro test, constant variance, Levine test. And for each design, you need to be familiar with the statistical model. For each design, you should be able to interpret the R outputs. For each design, you need to be familiar with the layout of the design. And also you need to be familiar with the differences between designs. And if you understand each design, so you understand the differences between designs. Okay. I hope I do not miss anything. So let's start by chapter 4. In chapter 4, we covered many designs. We covered, I think, 4 designs. This one is the first design we covered is complete randomized block design. Complete randomized block design. In this design, we have two factors, one blocking factor and one treatment factor. So in this design, we have one treatment factor and one blocking factor. And the requirement of this design, these two factors shouldn't interact. It shouldn't interact unless you are able to test each treatment more than one time within each block. But if you are testing each treatment only one time within each block, it means the block has number of units equal number of treatments. In this case, there is no interaction between the treatment factor and the blocking factor. No interaction between the treatment factor and the blocking factor. This is the requirement of this design unless you are able to test all the treatment, test each treatment more than one time in each block. So for example, if we have 4 treatments, let's say we have 4 treatments, T1, T2, T3, T4. These 4 treatments can be the 4 levels of the treatment factor. In general, can be a combination between all the levels of all the treatment factors. So in this case, if you have 4 treatments, each block should be big enough to test all the treatments randomly, maybe T1, T2, T3, T4. The second one maybe T2 the first, and then T3, and then T1, and then T4. So the last block can be used to test the 4 treatments. So this is block number 1, block number 2, up to block number B. So assuming we have B blocks, it means each treatment tested B times. And the statistical model in this case is Yij equal I for the treatment factor, how many levels, how many treatments. J is how many blocks, how many times each block, each treatment tested. So mu plus tau I, the effect of the treatment factor, plus beta j, the effect of the blocking factor, plus epsilon ij, and I equal 1 to up to A, number of treatments. J is 1 to up to B, number of blocks. So, and also you should be able to know the relationship between the values in the ANOVA table, like you divide the sum of squares by the degree of freedom, you get mean square, you divide mean squares by the mean square error, you get F values, and then get P values, and so on. So you need to be familiar with the output of R of ANOVA, and you need to familiar with the assumptions. And again, there are the three assumptions: the independent, constant variance, normality. You should be able to tell the assumptions are satisfied or not using the graphs, and also using the tests. Okay, so this is the first design we covered in chapter 4. The second design is called the Latin square design. If you have any question at any time, please let me know. The second design is Latin square design. In Latin square design, we have two blocking factors and one treatment factor. So in this design, we have two blocking factor and one treatment factor. Is there any other requirements? There is a very strong assumption that there is no interaction between any two factors, the blocking or the treatment. So there is no interaction between any two factors. Why? Because there is no degree of freedom left to test the interaction. And so we are not able to test the interaction, so we should assume that there is no interaction. All the interaction is not significant. So what about the statistical model? The statistical model is I for the first treatment factor, J for the second treatment factor, I for the first treatment factor, J for the first blocking factor, K is for the second blocking factor, equal mu plus tau I, the effect of the treatment factor, plus alpha J plus beta K, or you can use any notation, but you need to use three different notations, plus epsilon I J K. I is 1, 2, up to the number of treatments. Let's say P, because all of them are the same, have the same number of levels. Like we have two blocking factors, one treatment factor, all has the same number of levels. Assume the number of levels is P. So J equal 1, 2, up to P. K equal 1, 2, up to P. So the requirements are there is no interaction between any two factors, and we have two blocking factors and one treatment factor. Let me give you an example. The example of 3 by 3, it means we have three factors, one treatment factor and two blocking factors, each has 3 levels. So in this case, we assume the rows are the levels of the first blocking factor, and the columns are the levels of the second blocking factor. And now how do I assign the treatments? We assign them such that each treatment should appear only one time within each row and appear only one time within each column. So one of the random assignment is A, B, C, B, C, C, A, B. So when you look at these treatments, treatment A, treatment B, treatment C, or you can call them T1, T2, T3, it's up to you. Each treatment appear only one time within each row and appear only one time within each column. This is one of the layouts or one of the random assignments of the treatments. And also you should be familiar with the output of R about ANOVA. You should be familiar with the assumptions. Again, there are three assumptions. The three assumptions are tested and covered in all designs. So this is the Latin square design. Any questions so far? Okay. The third design covered in this chapter is Greco-Latin square design. In Greco-Latin square design, we have three blocking factors and one treatment factor. And the assumptions are our requirements that there is no interaction between any two factors. If we have three blocking factor and one treatment factor, it means that we have four factors, no interaction between any two factors. This is very important because we cannot test this one. So we assume it is not significant. So there is no interaction between any two factors. And the statistical model is I for the first blocking factor, J is for the second blocking factor, K for the treatment, and then L for the last the blocking factor, or any notation like you have I, J, K, L. So you have four effects for the four factors. So mu plus the four effects. Let's say theta I plus tau J plus gamma K plus xi L. So there is no interaction in the model because we assume the interaction is not significant, plus epsilon I, J, K, L. And I equal 1 up to P, J equal 1 up to P, K equal 1 up to P, L equal 1 up to P. So we assume all the factors have the same number of levels, and there is no interaction between any two factors. So let me give you an example. Like if you have three blocking factors and one treatment factor, each has three levels. So layout will be like this one. The first treatment factor levels are the rows. Second treatment factors levels are the columns. And the third blocking factor, we use notations like alpha, beta, gamma. So we need to assign these alpha, beta, gamma. So alpha, beta, gamma. Let's say beta, gamma, alpha, alpha, gamma, sorry, alpha, beta. So this one is a combination of the three blocking factors. The first level of the first blocking factor, first level of the second blocking factor, and alpha is the first level of the third blocking factor. For these three combination, we assign a treatment, let's say A. Do the same for all the others like B, C, say C, A, B, and then B, C, A. When you look at this layout, you will find each treatment appeared only one time within each row and only one time within each column. And something else, each combination or each pair of the treatment factor and the third blocking factor appear together only one time. Like A alpha repeated only one time, A gamma repeated only one time, C beta repeated only one time, and so on. This is one of the requirements. So this is the Latin square design layout. And then you should be familiar with the ANOVA or ANOVA table from our software, and you do not include the interaction because we assume it is not significant, and you should be familiar with the assumptions. Again, 3 assumptions: independent, constant variance, normality. So this one is Greek-Latin square design. Guys, if you have any question at any time, please let me know. Any questions so far? Okay. And then the next design we covered is balanced incomplete block design. Balanced incomplete block design. I need to have a new page. Well, the link for the new page disappeared. Okay, now I have. So the next one is balanced incomplete block design. In balanced incomplete block design, we have one blocking factor and one treatment factor. But this one should be the complete randomized block design. The difference between complete randomized block design and the balanced incomplete block design, that in the balanced incomplete block design, the block is not big enough to test all the treatments. If the block is big enough to test all the treatments, you should work with the complete randomized block design. But if it is not big enough to test all the treatments, you should work with the balanced incomplete block design. So let's assume that we have 3 treatments, T1, T2, or 4 treatments, T1, T2, T3, T4. But the block is not big enough to test all the 4 treatments, but it is enough to test 3 only treatments. So the first block can be used to test treatment 1, treatment 2, treatment 3, for example. The second block can be used to test the 3 treatments, let's say T1, T2, T4. The third one also is big enough to test only 3 treatments, let's say T1, T3, T4. One more block big enough to test 3 treatments, T1, T2, T3, T4. This one is called balanced incomplete block design. To be balanced, there are 3 assumptions. There are 3 requirements to be satisfied. So this is the layout of having 4 treatments, 4 blocks, but each block is not big enough to test all the 4 treatments, can be used only to test the 3 treatments. The requirements to be balanced incomplete block design are: the first one, each block or the blocks have the same size. So in this case, each block has only 3 units. So they have the same size, 3, 3, 3. The second requirement is each treatment repeated the same number of times. Each treatment repeated the same number of times or tested the same number of times. So let's see the second one is satisfied or not. Let's say, look at T1. T1 repeated or tested how many times? 1, 2, 3. T tested how many times? 1, 2, 3. 3 tested how many times? 1, 2, 3. 4 tested how many times? 1, 2, 3. So each tested the same number of times. The third requirement at each pair of treatments appear together the same number of times. So let's see T1, T2. T1, T2 appear how many times together? 1, 2, and 2 times. 1, 2, 1, 2, 2 times. So all the others should appear together 2 times. What about T2, T3? T2, T3, 1 time. 2 and 3, 1 time, 2 times, and so on. So all the pairs should appear the same number of times. If these 3 conditions are satisfied, we can say this one is balanced incomplete block design. But if one of them is not satisfied or more than one, it is incomplete block design. But the balanced incomplete block design is better than the unbalanced incomplete block design. What about the statistical model? It is Yij equal mu plus tau I plus beta j plus epsilon ij. We assume there is no interaction between the treatment factor and the blocking factor. This is why we do not include the interaction in the statistical model. Y equal 1 to up to the number of treatments. J equal 1 to up to n, the number of times each treatment tested. This is the statistical model. And you should be able to interpret and read the ANOVA table from R. Should be able to tell the assumptions of the model are satisfied or not. 1, 2, 3 again. This is the balanced incomplete block designs that we covered in chapter 4. Those are the designs covered in chapter 4. Any question about chapter 4? Okay, chapter 5. Chapter 5. I need to add a new page. Let's add many, so I don't need to add every time. Okay, chapter 5. Chapter 5 is factorial design. In chapter 5, we have many treatment factors, any number of treatment factors, because in chapter 4, we had only one treatment factor, but we increased the number of blocking factors. But in chapter 5, now we increase the number of treatments. So maybe 2 treatment factors, 3 treatment factors, 4 treatment factors, any number of treatment factors. For example, if we have 2 treatment factors, let's say one is A and the other one is B. And the first one maybe has some number of levels, any number of levels. Second one has any number of levels. So the statistical model, now this is our first time to have more than one treatment factor. So the statistical model should be Yij K, I for the first treatment factor, J for the second treatment factor, K for replicates, equal mu plus tau I plus beta j plus tau beta ij. This is our first time to include the interaction because we have enough degree of freedom to estimate the interaction and test the interaction also. Plus epsilon I j k. I is how many levels for the first treatment factor A? Maybe A levels. J is the number of levels of the second treatment factor, 1, 2, up to, let's say, B. K is number of replicates, may 1, 2, up to little n. This is a statistical model. And the layout, there are many ways to graph the layout. One of them is use a two-way table. Like the rows are the levels of the first treatment factor. Let's say we have two treatment factors. A has 3 levels. B has 3 levels. Let's say make them 4 because I make 4. Let's make them 3. Okay, 3, 3. So let's see, this is the first level of the first treatment factor, and then second level, and then third level. And then the first level of the first treatment factor, second treatment factor, second level of the second treatment factor, third level of the third treatment factor. So each combination is a treatment. This one is a treatment. And each treatment tested many times, let's say 4 times. So let's have 4 squares. This combination or this treatment tested 4 times. This one tested 4 times. This one tested 4 times. This one tested 4 times, and so on. So 4 is little n. So in this case, it will be Yijk equal mu plus tau I plus beta j plus tau beta ij plus epsilon ijk, and I equal 1, 2, 3, j is 1, 2, 3, k is 1, 2, 3, 4. This is the layout of the design. But some people use the trees like this. The first treatment factor has 3 levels, second treatment factor has 3 levels, and so on. And then each treatment tested 4 times. Each treatment tested 4 times, and so on. To the last one, each treatment tested 4 times. This is the layout. And we covered in this chapter the interaction plot to see if there is some interaction or not, because we included the interaction in the model. So you can test the interaction in the ANOVA table, or you can look at the interaction plots. If the interaction plots are parallel, or the lines are parallel, like this one, it means there is no interaction between the two treatment factors. But if there is some intersection, like this is the first one, and maybe this one is the second one, maybe this one is the third one. So it means there is some interaction between the two treatment factors. And in the ANOVA table, you should be able to include the interaction and test the interaction, and should be able to explain and interpret the results. In the ANOVA table, you will have, for this example, 3 p-values. Which one you should start with first? You should start by the p-value for the interaction. Because if as interaction is not significant, you can test each treatment factor separately from the other. You can look at the other 2 p-values. But if the interaction is significant, when you do multiple comparison for one of them, you look at the, you should do multiple comparison at some specific level of the second one. So if you have A and B, and you found AB is significant, when you do multiple comparison for A, you do multiple comparison for A at some specific level for B. And the same thing for B. When you do multiple comparison for B, you do multiple comparison at the some level of A, and so on. And the last thing, always, the assumptions are the same again, 3 assumptions as before. This is the chapter 5. So why we moved from chapter 5 to chapter 6? Because we found that in chapter 5, if we work with many treatment factors, each has many levels, the number of treatments will be very big. So the number of experimental units needed is much bigger than our resources. So maybe so this is why we moved from chapter 5 to chapter 6, because we need to save some resources. So so far, actually, we saved resources using 3 methods. The first method, we go from any number of levels to only 2 levels. So go from chapter 5 to chapter 6. And then in chapter 6, we dropped replication. So we saved the resources. In chapter 8, that is not covered in this exam, we worked with half of the treatment or 1/4 of the treatment, so we save much resources. Because sometimes one experimental unit costs a lot. Sometimes one experimental unit costs more than $1 million, so they need to save resources. So this is chapter 5. Come on, where is found it? Okay, guys, if you have any question, please let me know.
So it was just that one. It was just that one design for chapter 5.
Yeah, it is one design only. It is this design in chapter 5 is complete randomized design that we covered in chapter 3, but we extended this one to any number of treatment factors. So it's still complete randomized design with 2 treatment factors or 3 treatment factors or 4 treatment factors or 6 treatment factors. So this is generalization of chapter 3. So it's only one design, as you said. Any other questions? Okay, chapter 6. It is 2 to the power k factorial design. It means this is the number of treatment factors. And each has 2 levels. And this is the number of treatments. So when we work with more than 2 levels, we found that the number of experimental units needed is very big. This is why we decided to work with only 2 levels for each treatment factor. This one saved much resources. So how do I select the 2 levels? If the variable is categorical or the variable is nominal, you select 2 levels are far away from each other as much as you can. Like if it is educational level, you select 2 levels, like someone is college and someone doesn't know how to read, how to write. If this numerical variable, you select 2 values very far away from each other as much as you can. Like if temperature, you do not select temperature 77, 78. Select something like temperature 40 and temperature 90 or 70. So it should be far away from each other as much as you can to capture the true relationship between the treatment factor and the response variable. So in this case, each treatment factor has only 2 levels. What about the treatment, the statistical model? The statistical model, assuming we have 2 treatment factors, A and B, but in this case, each has only 2 levels. So number of combinations, number of treatments is only 4, 2 to the power 2 factorial design. And Yij k equal mu plus tau I plus beta j plus tau beta ij plus epsilon ijk. Looks like the same one in chapter 5. It is the same one in chapter 5, but the only thing is I is 1, 2, 2 levels only. J is 1, 2, 2 levels only. K is 1, 2 up to N. The difference is the number of levels for each treatment factor. In this case, we have only 2 to save much resources. And in this case, working with 2 to the power k factorial design will make everything easy. Like when I calculate the main effect and reaction effect is very simple. We use the idea of pluses and minuses. So we use the -1, +1, -1, +1 as the 2 levels for each treatment factor. And let me show you the table and how to calculate the main effect and reaction effect using the table that has pluses and minuses. Let's assume you have 2 treatment factors, each has only 2 levels. So we have a column for A. A has 2 levels only, and B has only 2 levels. So the treatments are the combinations. So this one is -1, -1. This is the first combination, the first treatment, and we call it 1. The second combination of the second treatment is +1, ±. So A is high only, so we call it A. The third treatment or the third combination is -+, and we call it B. The last combination of the last treatment is ++, and we call it AB because both are high. And then we collect data. We test -1, -1. We test low for the 2 treatments, and we calculate or measure the response. And maybe you have 1 replicate, so you have only 1 column for the response. Maybe you have 2 replicates, maybe you have 3 replicates. So you measure the response. If you measure the response only 1 time, it is 1 replicate. You measure the response more than 1 time under each treatment, it means you have replicates. So let's assume you have 3 replicates. So you measure the response under low 3 times, under high-low 3 times to the last one, ++, you measure the response 3 times. It means you have 3 replicates. 3 replicates. And sometimes if you would like, you can use these numbers to calculate the main effect and reaction effect, or you can calculate the sum. So you calculate the sum of these 3 values, the sum of these 3 values to the last one, the sum of these 3 values. So you can work with the totals, you can work with the original values, these ones. So how do I calculate the main effect of A? The main effect of A, for example. You calculate the average of pluses minus the average of minuses. So A has 2 levels, has minus and has plus. When the A is high, we have these 3 values and also these 3 values. Those are 6 values. You sum these 6 values, divide by 6, you give me the average when A is low, A is high. And when A is low, did I mention low first or high first? Let's do it again. Yeah, I mentioned plus first. So plus, you calculate the average of these 6 values, minus when A is low. So I have also 6 values, 1, 2, 3, 4, 5, 6, the average of these 6 values. So you calculate, and then you calculate the difference. That difference represents the main effect of A. If this difference is big, it means that the main effect of A is significant. It means that the 2 levels of A are different. But if these differences is small, it means when the main effect of A is not significant. It means the 2 levels are not different. When you go from one of them to the other one, on average, Y doesn't change. What about the main effect of B? Main effect of B, the same thing. B has 2 minuses and 2 pluses. You calculate the average under plus minus the average under minus. You get the main effect of B, the same thing. What about the interaction AB? To calculate the interaction of AB, you need to have a column for AB. How do I get the column of AB, pluses and minuses? You multiply A times B. So minus times the minus gave me plus, plus times the minus gave me minus, minus times the plus gave me minus, plus times the plus gave me plus. Again, I have 2 pluses and 2 minuses. So we calculate the average of plus, so the average of these 6 values, minus the average of minus, the average of these 6 values, to give you the interaction effect AB. If this interaction effect, if the value is big, the interaction will be significant. If the value is small, the interaction is not significant. In this case, we have a replication. It means we tested each treatment more than one time. In this case, you have plenty of degree freedom to estimate all the effects and test all the effects. Because we have much degree freedom, we have much information. So you can test the interaction, you can test everything. But if we have no interaction, assuming we drop replication, because we need to save more resources. In this case, there is a problem in testing all the effects. You will not be able to test all the effects. You will be able to estimate all of them, but you will not be able to test all of them. So let me explain this one. Let's assume we have two treatment factors. So it will be 2 to the power 2 factorial design. And this is the table again. A, B, A, B. And only one replicate. So this one is minus, minus, plus, plus, minus, 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 plus, minus, plus, plus, plus. So you tested each treatment only one time. You have only one value under each combination or under each treatment. So how do I estimate the main effect of A? It's very simple. You calculate the average of pluses. So the sum of these two values divided by 2 minus the sum of these two values divided by 2. You get the main effect of A. Do the same thing for B. Do the same thing for AB. Will I be able to estimate all these ones? You will be able to estimate all these ones. You estimate the main effect of A, main effect of B, main effect interaction AB. But the problem is I will not be able to test all of them. Why? Because I need to estimate sigma square also. So this one needs at least 1 degree freedom. And the degree freedom left is 0. What do you mean by degree freedom left is 0? The total degree freedom is the total number of values minus 1. And I have 4 values. So the total degree freedom is 4 minus 1 is 3. So I can use the 3 degree freedom to estimate these 3. But there is no degree freedom left to estimate sigma square. So how do I solve this problem? The only way you can do is you need to remove at least one of these 3 effects. So which one I should remove? You should remove the ones that most probably is not significant. And also you do not have a research question in your mind about this effect as a researcher. So how do I remove at least one? We covered many methods. We covered normal probability plot. The effects that on the straight line should be included and the ones far away from the straight line should be excluded. Maybe this one is AB, this one is A, this one is B. So this one means include this one on, oh sorry, this one is not logic. Like this one is maybe A and this one may be AB and this one may be B. So in this case, you include only B effect in the ANOVA table and remove the others. So you remove 2, you gain 2 degree freedom to estimate sigma square. So maybe you can work with the normal probability plot or have normal probability plot or Pareto plot. Pareto plot order the effects from the biggest one to the smallest one and give you something called margin of error. And you can add anything above the margin of error. So this one may be B. Or you can use a reference plot. In reference plot, graph half of the standard normal distribution. And it shows which effects are close to 0. Maybe this one is BA, when this one is AB. And this one is B. And also we covered effect test. Effect test give me p-values for each effect, and I include the only ones, the significant ones, the ones has p-value less than 5%, and exclude anything has p-value greater than 5%. So after you remove at least one, in this case, if this is your case, you remove 2, So you gain 2 degrees of freedom to estimate this one. And you include only in the ANOVA table, only this one. And now you solve the problem. But I save much resources. I saved much resources by having only one replicate. But the problem with this one is outliers. Because you test each treatment, when you have one replicate, you test each treatment only one time. So you should be very careful when you test the response. You shouldn't do any mistakes when you measure the response. And also when you enter the data in Excel, you should be very careful because you shouldn't do any mistakes. And also in this one, you should be familiar with the ANOVA, R from R. And also you need to be familiar with the assumptions. So assumptions are on all the designs we covered. So you need to test the assumptions all the times. So if you have no replication, you can save much resources, but the problem is there is no degree of freedom left to estimate the sigma square. So we need to remove at least one of the effects. But so far, up to this point, we always check the 3 assumptions and we find they are satisfied, they are satisfied, they are satisfied. But what if the assumptions are not satisfied? Whatever the design you are working with, maybe you are working with complete randomized design, complete randomized block design, balanced incomplete block design, Greek Latin square. What if the one of the assumptions is not satisfied, especially normality and or constant variance? You need to find some transformation. What do you mean by transformation? You need to change Y to be something else. What do you mean by something else? I mean, maybe you take the square root of Y. This one is called the transformation. You take the square root of all the values. Or you take the natural log of Y. Or maybe you square the value of Y. Maybe is 1 divided by square root of Y. There are infinity number of transformations. Which one will fix the assumptions? You need to use a function called Cox-Bucks function. Cox-Bucks function will recommend what are the transformations that make normality satisfied. And actually, when you fix the normality, most of the time it fixes the constant variance also. So this function gave you a graph like this one. And it gave you lower limit and upper limit. All these values between this upper limit and upper limit are some values may fix normality. So these values are called lambda, which is this one. So you need to find lambda that satisfy normality. So y will be to the power lambda. The square root means lambda is 0.5. Natural log means lambda is 0. To the power 2 means lambda is 2. 1 divided by square root of Y, lambda is negative 0.5. So you look at this lower limit and upper limit and select something close to the maximum of the curve, because this curve is the graph of the log likelihood. So the function Cox-Bucks graph the likelihood over the range from -2 to 2. And it gave you lower limit and upper limit of all the possible values for lambda that satisfy normality. But you should select something nice, like if this one is something like this one is 0 and this is the maximum of likelihood. Do not select something like -0.001. What does it mean, -0.001? Can I select 0? You can select 0. This one is nice selection, like 0. Lambda equals 0 is natural log of Y. Or you can select 0.5. This one is nice, square root. Select -0.5. Select anything within the range that makes sense. But do not select something weird, like do not select something like lambda is 0.33. What does it mean? Y to the power 0.33 is not nice. This one is to the square root of the third, I think. This one is also okay, but do not select something like 0.12. See my point? So you can select any value within the range of the confidence interval, but you should make sense. And this one, once you transform the data, and once you apply the transformation, and you do everything from the beginning again, you will find the assumptions are satisfied. So this is chapter 6. Now let's go to the last chapter, which is chapter 7. Any questions so far? Okay, chapter 7. This one is 2 to the power k is 2 to the power k factorial design plus blocking factor with no replication. So chapter 7 covers this idea that we have 2 to the power k factorial design. It means we have k treatment factors. Each has 2 levels to save resources. But we have a blocking factor. We include them because 2 to the power k factorial design, it means k treatment factors. There is no blocking factors in chapter 6. But in chapter 7, we include blocking factor. We include blocking factor, and we assume the blocking factor has 2 levels or 4 levels and so on. So with no replication to save much resources. What about this case? The problem with this case is there is no many degree freedom to estimate everything and test everything. But we need to save resources. So let me give you an example. Assuming we have 2 treatment factors, A has 2 levels, plus minus, B has 2 levels, plus minus. So in this case, we have 4 combinations. We have 4 treatments. Let's call them T1, T2, T3, T4. Or you can call them 1, A, B, AB. Those only notations. Or you can call them A plus, B plus, A minus, B, and so on. So in this case, if you have many blocks, and each block is big enough to test all the treatments, will be complete randomized block design. If you have many blocks, and each block is big enough to test all the 4 treatments, this is complete randomized block design. If you have many blocks, each block is big enough to test something like 3 treatments, and you have many blocks to make it balanced incomplete block design, work with the balanced incomplete block design. But sometimes we have only 2 blocks. We have only 2 blocks. And each block is not big enough to test all the treatments. Each block is enough to test half of the treatments. In this case, we have 4. So each block is big enough to test only 2 treatments. So this is the first block, this is the second block. So how do I test 2 treatments using this block, 2 treatments to test these 2 blocks? These 2 treatments to test within this block. So I have 4. I have 1, A, B, A, B. How do I arrange these 4? There are many ways to arrange these 4 within these 2 blocks. Like one of them is, this one is 1, test AB. This one, test A, test B. This is one of the combination or one of the arrangement. So what is the problem here? The problem here, I have only 4 measurements. I will measure the response only 4 times. So I will have 4 values only. So the total degree of freedom will be 4 minus 1, 3 degree of freedom. So how do I use this 3 degree of freedom? I hope I have many degree of freedom, so I can estimate all the effects, test all the effects. How many effects in this case? I need to estimate the main effect of A. the main effect of B, the interaction effect AB, and the blocking effect. They are 4, but I have only 3 degree freedom. So how do I solve the problem? Because in chapter 6 with no replication, I was able to estimate all the effects, but I was not able to test all the effects. So I remove one and then I tested the others. But in this case, it's a bigger problem because I'm not able to estimate all of them. What should I do? How do I use 3 degree freedom to estimate 4 effects? You should use the idea of buy one, get one free. What does it mean? It means I should select 2 and I will estimate these 2 by only 1 degree freedom. By only 1 degree freedom. So maybe this one and this one was 1 degree freedom. Maybe this one was this 1 degree freedom. Maybe this one was this one, only 1 degree freedom. So which one buy one, get one free? It depends on the arrangement. Actually, this arrangement will make AB confounded with blocking effect. What do you mean by confounded? It means the estimation will be the same. It means these 2 will be used to estimate these 2. I will use only 1 degree freedom. And this one, 1 degree freedom. And this one, 1 degree freedom. So now I solve the problem of the estimation. So how do I select these 2, and these 2, such that I make the highest order of reaction confounded with the blocking effect? You look at the pluses and minuses table. So how do I select? Let's go to the plus and minus table. So this is a pluses and minuses table when we have 2 treatment factors, each has 2 levels. This is A, this is B, this is AB, minus, minus, plus, minus, plus, minus, plus, plus, plus. And this one will be plus, this one will be minus, this one will be minus, this will be plus. And we measure the response only 1 time. So we have 1 value, 2 values, 3 values, 4 values. So how do I select half of the treatments? This is the treatment 1, this is the treatment A, this is B, this is AB. How do I select half of the treatments and I assign them to the first block, half of the treatments to be assigned to the second block, such that I make the blocking effect confounded with AB? It means it's the same estimation. If you'd like to make AB confounded with the blocking effect, look at the column of AB. Select the treatment that has pluses in this column to assign to the first one. So I look at this one is plus and this one is plus. So I select these 2 in the first block and I select these 2 in the second block. This way will make the blocking effect confounded with the AB effect. Because when you look at these, the columns of these ones will be almost the same, will be the same. So when you estimate the blocking effect, will be exactly the interaction AB. So now I solve the problem of the estimation. So now I will use the 3 degree freedom to estimate the 4 effects. Can I test all of them in the ANOVA table? You cannot test all of them in the ANOVA table because we need 1 more degree freedom to estimate sigma square. It means after the estimation, I need to remove at least 1. So how do I remove? Again, as we have done before, you go to normal probability plot or have normal probability plot or Pareto plot or the have the reference plot or the effect test. So you can use these tools to remove at least 1 of the effects, and then you go to ANOVA table or you include only the effects recommended to be included in the ANOVA table. And then you test the assumptions. Again, if they are not, if any of them is not satisfied, you need to find some transformation. So this is the end of chapter 7. I'm done. Any question? Any question? Okay, if there is no question, so I'm done. And good luck in your exam. I hope you do great, better than exam one, and enjoy your life. I will record this one. I will upload it on Canvas. So if you'd like to watch it again. Thank you guys and have a great day.
Thank you. Have a good weekend.
You too.
Thank you.
Everything.
Thank you.
And now.